Great. Do I need to use this?
Uh, okay.
Testing. Can everyone hear me, or should I use the mic? No? Okay, great. Hi, everyone. My name is Eric Jang. I lead AI at 1X. I'm presenting a lot of work done by the excellent AI team and hardware teams and software teams, and I basically just made the slides. So I'll be able to answer some questions, and other questions maybe I won't know the details of, but I'll try my best. And the title of this talk is Moving at 1X Speed, and I'll just talk about how we think about the AI control and the various layers of the control hierarchy. Thanks to the organizers for inviting me to the workshop. So a little bit about us. We make one product, Neo. It's a home humanoid robot, and we're doing some testing in employee homes, doing basic chores in the home. The company was founded in Norway, but we have an office presence in Palo Alto now, with big headquarters, putting all the hardware and software and AI and operations together. So I was thinking a little bit about what to talk about, and I'll share a bunch of work we've done at 1X, but I also want to kind of think a little bit forward-looking in how I think about a recent question I've been getting a lot, which is about System 1 and System 2 architectures in robotics. So how many of you are familiar with this book, Thinking Fast and Slow? It's like a popular science book that talks about this idea that the human brain has two systems. There's a System 1, which is fast and intuitive and automatic, low level and reactive, and that's System 1. And then System 2 is this more deliberate, slow reasoning, performs search, high level decision making. And in reinforcement learning and robotics and control, this theme of having these two modules, System 1 and System 2, interacting with each other comes up again and again and again in many different flavors, ever since very early days in robotics, at least going far back to like 1980s, maybe more than that. So then there's a question of like, what are these boxes? Like in robotics, what is the specific instantiation? What comes out of System 1? What is System 2 doing? How are they actually different? So I want to talk a little bit about that. One naive way to start with the System 1 and System 2 architecture is to take the smartest VLM like, I don't know, ChatGPT 4o or Gemini, and this is a pretty general agent, and so let's use this as our System 2. It's a kind of smart thing, and also very big, so it's going to be slow. And let's attach to that some tool call, which is a robot, and it'll just make tool calls to a robot, send language to a robot, and the robot policy on the robot executes some more dexterous high frequency task. Right? So maybe this thing is emitting language, and this sub-goal condition policy spits out joint angles, and that's your System 1 and System 2 decomposition. That's an idea that we were pursuing at some point last year, where we were trying to take our policies that we were training and coordinate them with a VLM. But when you actually try to implement this, a lot of tricky details show up. So, for example, let's, is the VLM going to be doing any thinking or searching, right? Like AlphaGo style, or maybe using DeepSeek style reasoning tokens? That's one question. And if the answer is yes, does that imply that your System 1 policy is not going to do any thinking? Yes, no, unclear, right? So then another thorny question that comes up is that how does the VLM know what the tools do? So let's say your sub-goal condition policy can do 100 different tasks. How does the VLM actually know if a tool is appropriate, or if it'll work, or if it doesn't work, what tool you should use instead? There's a lot of details that matter here. If people are familiar with the SACAM paper, there is ways to communicate stuff up the chain by sending affordances back. But again, this is a little bit complicated in the modern VLM days. How do you communicate in a sort of richer format besides like a queue function what is possible for the VLM? And if you're interacting with the world as an generalist agent really should be, it's not clear how you send information about what tools work and what doesn't. So that's all kind of messy. And then finally, there's this question of like, do you train this whole thing end to end, right? Like if you have this thing be an end-to-end differentiable network, you could just backprop through the whole thing and train it jointly. But then in 2 years, when the NVIDIA GPUs get 10 times faster, and you can put all of this on board, like, is that now your new System 1 policy, or is there any, is the System 2 thing really just a function of like what is too slow and what is too fast? I think these are all questions that come up, and it makes it sort of murky in terms of designing like a strategy around high-level and low-level thinking. So I wanted to share a little bit about how we at 1X think about this problem, or at least how I think about it. And this is a workshop, so this is really me workshopping this idea. I don't have a super strong conviction on it, but I'd love to get feedback on this after the talk. Let me go back to like a more simpler time when we had a very good understanding of high level and low level control. So if you consider like a self-driving car problem, it is very often broken down starting from your high level route plan, which is refreshed every second or so. It gets, while the car is driving, uses vision and LiDAR and radar and whatnot to predict some kinematic path in ego frame. And this is done at somewhere from 10 to 100 hertz. And this is predicting position waypoints, right? Like where should the car be in space relative to the car? And when you have this plan, then you try to track it. The car is a moving vehicle with inertia and mass, and you have to apply controls to make sure that you're tracking this. And so that's where the low-level dynamics come in. And so in dynamic control, you're doing this at 100 to a kilohertz, and you're operating in forces or acceleration or velocity, right? So this thing does not care how much the car weighs. This one does. So you can draw parallels here to humanoids. A natural breakdown here would be there's a high-level semantic plan that's like the smartest VLM that you have. It spits out text tokens. A common task that people think about for high-level, low-level stuff is subtask decomposition. So maybe you'll take a long horizon task like bring me a Coke, and then it'll break it down to like go to the table, pick up the bottle, hand it to a person. And these get fed to a policy that does the kinematic plan, usually a visual servoing policy. And so this runs at 10 hertz. And this generates your position waypoints, right? Like these green hand poses correspond to predictions of where Neo, a robot, wants to move its hands. And once you have the kinematic plan, then you have some controller, for example, inverse dynamics, or maybe an RL controller that tries to track these accurately while fulfilling many other objectives like not falling over and so forth. And so here you're dealing with force, Coriolis effects, acceleration, velocity, and this happens at a high frequency. So there's different scales of control speed, and this leads to a very natural breakdown of how we separate high level and low level control, which is based on just how fast you have to react. Oh, right. One thing I forgot to mention is that actually, in robotics, there's also physics. Like there's a physics control that goes underneath the idealized forces and accelerations you want, which is like the actual control of the motors. If you are using, high torque density, low speed motors, as we do, they are actually non-trivial to control, and so you need to come up with clever ideas to actually move them correctly. And a lot of people think that it's silly to try to do this end to end, but who knows, right? So let's move on. Another way to think about decision time scale is not about what is thinking or fast and slow, but really just on a humanoid, how fast do certain decisions need to be made? Because a humanoid is not like a statically stable thing that you can choose to move however slow you want. It really matters that it maintains balance. A lot of its behaviors are quite dynamic. So this is a hardware platform that really reminds you that certain decisions need to be done quickly. So one way to rephrase the decision time scale is how bad can things get if you don't react for a certain amount of time, right? On the dynamic planning level, it deals with forces. So maintaining balance is something that matters at the level of milliseconds, not hundreds of milliseconds. If you are a very stiff system and you are like, let's say, wiping a table, you want to make sure that you don't suddenly push down too hard into a table. And so for like contact-rich tasks, the time scale is pretty short, especially if you're quite stiff. Slipping matters a lot. This happens when you're walking, as well as maybe grasping objects. And of course, when you're tracking errors, you don't want to be tracking at the hundreds of milliseconds. You want to track things carefully at tens or even ones of milliseconds. And for very dynamic tasks like parkour or catching a ball, that's also very dynamic. At the kinematic level, it's not that different from dynamics. It's just that things are generally slower. So for example, if someone is pushing an object away from you, it's okay to recover at about 100 millisecond latency. But if you're taking 1 second to react, that's kind of not a great experience from like a robot policy. So for very dynamic policies that can kind of adjust or regrasp, that's where hundreds of milliseconds is kind of ideal, especially if there's opportunities to recover in that time span, right? So for example, if you're folding a shirt, there are scenarios where recovering within 100 milliseconds is fine, but recovering within 100 milliseconds is not fine because the shirt dynamics are just going to be too chaotic within that span of time. So being able to react and bound how bad things get in your state space is where like manipulation tends to be around 100 milliseconds. And finally, on semantics, that's an area that I think robotics has not really prioritized speed. A typical case of high-level planning requiring replanning is when you, for example, fail or succeed at your previous task. And that's sort of like a bottom-up notification. But maybe a new instruction comes in, and maybe you're like a voice assistant, like ChatGPT or a Google Assistant, and you want to respond quickly to the new user request. And in a contrived case, like high-level plans actually can change arbitrarily fast. It's just that we aren't testing our robots in these scenarios. So if you have a case where you're saying like, hey, Neo, catch, you throw it a ball, this is a case where it needs to create a new task and execute a completely new plan really, really fast. We just don't test our robots in this scenario yet. And another one would be like if you're playing blitz chess or blitz chess plus chess boxing, then of course things change very quickly on a semantic level. So how do we tackle some of these problems? Well, we have very compliant, low inertia, low reflected inertia hardware. So that actually allows us to solve these first two problems mostly just from the hardware. So if we're trying to grasp open a door and you kind of pull in, the kinematic plan pulls in the wrong direction at 100 milliseconds of sort of delay, it's okay because you can actually pull in the wrong direction and your hardware will sort of give you that compliance. Whereas if you had a much stiffer robot, then you have to actually know that you're pulling in the wrong direction much, much faster, right? So hardware makes a huge difference in terms of being forgiving in the time scale that you can do control. And that helps us a lot, especially with things like RL and the behavior policies. Of course, compliance doesn't help you stay balanced. So we still need RL control to maintain balance and handle the dynamics there. And I'll talk a little bit about how our RL controller works for things like tracking and not slipping. And then we don't do parkour currently. On the kinematic level, we've been training a VLA that I'll talk about, and that's mostly your classic VLA architecture that does diffusion for whole body manipulation. And then on semantic plan, that's something that we're working on, but I don't have anything in this slide deck that talks about kind of semantic planning at the moment. Okay, so I'm not sure if this is a hot take, but I'll just say it anyway, and maybe it's obvious or maybe it's not obvious. But the way I think about system 1 and system 2, or this question of like high level and low level policy, is really about the time budget for what you need to compute and the compute budget that you have for it. And this dictates what your architecture looks like. And it may end up looking like a sort of system 1, system 2 decomposition, but it is purely, in my opinion, a function of just the compute resources you have and the cost of your sensing and the cost of and how fast your hardware system needs to react to the scenarios that you're deploying your task in. So these are the sort of inputs, and then based on these inputs, you can kind of determine what your architecture looks like. That's the sort of claim that I'm trying to make here, in terms of how we build these generalist architectures. So if you assume it's 1x, let me walk through an example here. So this is based off of like numbers taken from what we use. So assuming you need to do tasks at 1x speed and you're not allowed to really slow down the environment dynamics, and things move at the normal speeds that humans encounter them, then let's say you're trying to do some general tasks and you have a VLA that has 200 milliseconds to react to object positions that are changing relative to your hand because you're doing a visual servoing task. On a embedded GPU like a Jetson Orin, you can squeeze something between 1 to 3 billion parameter transformer encoder on here, not a decoder, but an encoder. And if you do this, you have roughly enough token budget for like a low resolution image, sub 512 by 512, some temporal history, some tokens for proprio. Do I have any proof that this is true? No, this is just empirically what we kind of find that we have budget for. And I'm sure that there are ways to, with more optimizations, squeeze a lot more in one direction or the other. But roughly, this is the envelope that we work with. So if you have, so this is the budget you have. And if you need to make decisions at, let's say, 100 hertz because they need to be smooth, then this implies that you must, for example, do, let's say, 5 hertz inference on images, but have stale vision to update your actual trajectory plan. So for example, maybe you'll use a faster loop that processes your proprio tokens because you get them very quickly and they're updated, but you have a relatively slow, infrequently run encoder that runs at a slower frequency. Or you do something like you do 5 hertz inference, but then you just do a naive interpolation at 100 hertz. That's the sort of options that you have. And if this is also with the assumption that if you want to fully utilize your hardware, then then the compute budget you have and the sensors and the tasks that you have more or less determine your architecture. So this is our architecture. It's actually not fully using the compute yet, but it's generally the shape of what we find reasonable for our current set of tasks. We call it Redwood. It's just the sort of brand of our AI, and it's a whole body control. So it predicts the upper body joint angles, the walking commands, the hand closure, the neck, and the pelvis height and the pitch and roll. So it allows it to control the whole body. To our knowledge, it's one of the first models that kind of controls a whole humanoid robot end to end with imitation learning. In addition to that, to make it fit well on a small network with a small number of parameters, we found that it was really helpful to have a bunch of auxiliary perception tasks to ground the representations during training. Here's an example of where things might go. This is not our current architecture, but this is illustrating what I mean with optimizing your architecture and your system 1, system 2 decomposition for your hardware. If you try to squeeze as much compute out of your embedded GPU as possible, you might end up with a scheme where, let's say you have diffusion, some number of steps of diffusion, the biggest transformer that you have here emitting the required frequency of updates that you want to react to let's say, visual servoing, and then you need to cache your bigger things at a lower frequency, right? And the separation of things at higher frequency and lower frequency is what actually leads to this idea of a system 1, system 2 thing. So is this system 1 and this is system 2, or is this system 1 and system 2? I don't think it really matters. What this really emerges from is like the necessity of fitting things onto compute, and you actually might end up with a larger cascade than just 2 blocks. So here's an example of what Redwood can do. We've been testing it in the home, and this is like an end-to-end mobile manipulation sequence where we instruct Neo to go and pick up a drink and give it to the user. And this is all just one model running autonomously. So the same model can also generalize to unseen objects, with the exception of this object here. All the bottles in the data set are not in the training set, and the positions are all just randomized on the table in the home. And this is achieved by just using diffusion. So that we get a lot of that like retrial behavior with the inductive bias from that. Okay. It can also do whole body manipulation tasks like squat down and put some laundry away. This is one of the tasks that we think our users will care a lot about. And yeah, they're still quite atomic. They're not like the full chore yet, but that's what we're working towards. And finally, this is another example of a whole body manipulation task that illustrates the usefulness of compliant hardware. If our model's making mistakes, it's not going to yank its wrist off or break its fingers or damage the door, because the compliance in the arm helps. And you're not going to win against the door. All right. So what makes this all possible? Like how do we enable the data collection in the home and as general of a data set as possible? This is where the RL stack comes in. So we did a bunch of work on training RL policies. I very much agree actually with what Zen just said in the previous talk. PPO, motion targeting, sim to real, it's all standard stuff. But let me kind of talk about why the RL layer is important. This is the tool that enables our AI to see as many diverse states as possible. If you look at data sets like Ego4D, where it's a human doing the task, they visit so many more interesting states than what most bimanual manipulators and humanoids are able to collect today. And that is purely not because the humanoid is kinematically limited, it's because the software does not allow it to access the states. So we have a very big focus right now on enabling our data collection to actually get everywhere and bridging the RL layer with the teleops that we can get Neo into a lot of places. The classical approach to solving whole body control in humanoid robotics is to use a relatively beefy CPU to run a MPC in real time, and you basically plan in a dynamic simulator to make sure that you can achieve your goals, and you have to make sure that you characterize the system really well. This doesn't work super well in a home where things are super unstructured, objects are kind of all sort of soft and deformable, and it's not clear what you can step on and not step on. There's a lot of semantics in there, and finally, this latest generation of hardware is not as machined as carefully because we want to optimize for cost. So the modern paradigm that we're seeing is a lot more sim to real RL, And this covers for a lot of differences in hardware and allows us to kind of go for actuation approaches that are more scalable from a manufacturing perspective. So I want to show some early footage of what our RL policies looked like in the early days of us kicking off this effort. This was with Neo betas, and in October 2024 when we got the first sort of sim to real kinks worked out, and it was walking kind of like an old person, very stiff, very slow, a little bit unstable in different directions, and a lot of reward tuning. And this is what I would call like a RL 1.0 type of approach, where this has been done since like 2015 in ETH. Yeah, sysid was very important to get this working. And after this, we were like, let's make the behavior better. So we did some more tweaks, and we did a lot more reward engineering, and the behavior got better. But still, it was a lot of work to get a small incremental gain. And we were starting to realize that if we needed to do this amount of effort for every single task that we want to learn, it would just be a hugely complex endeavor. So how do we scale beyond that? This was one more iteration. This is still the same kind of paradigm as I showed, but you can see things are getting better, and we were able to add a sitting behavior here, which took an enormous amount of work to kind of design the state machine that transitions between sitting and standing and so forth, and walking. Okay, so around that time, we were starting to see some very promising works in robotics translating motion imitation from digital humanoids. A lot of the work inspired by what Zen has done to real robots. And we see very impressive demos. Like this is from Engine AI, where oh no, shit. I don't have internet. Okay, you're gonna have to take for granted what this does, but it's a dancing humanoid robot video where it does this really, really, really elegant dance. And this is like a single trajectory motion imitation work. So we're seeing evidence that RL can follow and track mocap trajectories to get really, really natural behaviors without a significant amount of reward engineering. And that's really beautiful. However, the limitation of this technique is that it's not obvious how to make it steerable from a teleoperation perspective, because all it does is replay the trajectory and track the kinematics, but it doesn't have a steerable interface. And naive attempts to just inject a steerability reward often really damage its ability to look natural, right? So we want to bridge the controllability of this RL 1.0 paradigm with this mocap reference tracking behavior on a real robot. Where and one difference between real robots and simulated characters is that real robots are way less stiff, so you can't just teleport to your desired position. You actually have to like overcome dynamics. Okay, so here's some work where we were able to train Neo to run following a single mocap trajectory, right? Just to prove that we can do something like the Engine AI dancing video. We weren't doing dancing, we were doing a few other behaviors. So here's another example from our recent video shoot. This is also single mocap reference following for an RL trajectory. You can see that the behaviors are very graceful, but this is not inherently useful in the home if we're trying to teleoperate them and collect useful data. So the architecture that we found to work really well is to come up with a two-level system where you have the RL controller tracking a input reference trajectory, and it tries to follow this. And this is a pretty standard approach. For example, you pass in the retargeted Neo reference from the AMAS data set or something, and you emit the motor torques to try to track it. This works, but how do you teleoperate this? Because at test time, we don't know how to produce a kinematically human-like trajectory using a Oculus device. The trajectories look very different. So what we end up doing is training a motion generator, a generative model that maps the input commands, like let's say a joystick command, to generate a one-to-many kind of mapping to the retargeted references. So if I'm pushing the joystick forward, it emits a kinematically beautiful trajectory, and then this one follows it, and then that achieves the sort of best of both worlds, where you can follow natural trajectories while still steering it around. And this is not an open loop system. It feeds back in its predicted state so that it kind of doesn't diverge. All right, so here's an early example from February where we started to get this to work. Now you can see that it like walks a lot more naturally, and this is controlled via VR. I'm running very short on time. Okay, let me Keep going. So here's more behaviors we can do now with the RL controller. This is all under one controller, but not a single network. So some of these behaviors use this approach and some of them are one-off policies, but we blend them all together so we can get Neo into all the states. Another ability we have now is kneeling and getting up. And this is very important in the home. If you want to bend down and pick something up under this table or unplug something from an electrical outlet, you can do that. And then it gets back up. Yep. Okay, so yeah, I wanted to comment that like this architecture is kind of like a system one, system two thing, but I don't know if I really call it system one, system two. This arises out of the necessity of computing. Okay, stairs. So we come up with a similar decomposition for stairs. We want to now put in vision into our RL policy so it can climb stairs from stereo RGB. We cannot process images in an image encoder at 100 hertz. So instead, we do the best we can, which is we feed it in at 5 hertz and hope that this thing can deal with it. And indeed, it can. But again, this looks like system one, system two, but it is arising out of necessity, not because I think that this is thinking and this is not. So here's some stairs. And to my knowledge, this is one of the first works that does like stereo depth to stair climbing control. Okay, I think we're really short on time, so let me just speed through the rest of this. Putting it together, this is the Redwood model, controlling the natural walking controller, and it is basically following around a soccer ball and trying to kick. So this is autonomous. Great. So generalist robot recipe. This is what I think should work, but again, I'm workshopping this idea. So write down what kinds of things that you need to react to and how fast you need to react to them. For each of these tasks, think really hard about what sensors are actually required to make the decision. And for each sensor, you need to process it from like a raw thing. So for example, images take a long time to process. And so you need to account for the cost of processing the raw data, not just the cost of acquiring the sensor. And my claim is that for a given fixed compute hardware, your multitask network in terms of all the balancing and kinematic and whatever task you need to do, this forms a pretty deterministic cascade with which you can allocate your parameters and your compute. And that's how you maximize your utilization of hardware. And so then the architecture that I think we'll end up having in the future for like multimodal real-time systems is going to be this cascade of nets where you have big nets that take a long time and small nets that are really fast, and this cascade of reaction times, and each of these blocks might react at different frequencies depending on what is needed in the environment. The frontier of what I think is a very interesting problem that I don't have a good answer for is how do you bridge really reactive things that depend on slow things? So for example, if you say like, hey, Neo, catch this, this might require some language processing, which maybe happens at 2 hertz, but it also requires something quite fast, maybe 10 to 50 hertz in terms of the ability to dynamically catch them. And finally, 2 possible futures as to how I see system 1, system 2 evolving. One is, we have these 3 levels that I talked about. I think the trend we're seeing is that these are going to get merged into a single model, so we won't have this 3-level hierarchy. Or RL starts to work a lot better, like for example, Zen's PDC work, where this thing starts to subsume more of this task. And I think both of these are very exciting directions to work on. And thank you for your listening to the talk.
Thank you for the talk. Very good work. And I just ask one thing, one very tiny detail. So in your visual base, they're timing. As you see, you have a global point cloud produced by your stereo depth module, or that's somehow encoded, then decoded, reconstructed.
The former.
The form. Okay, so you do have a module for that.
Yeah.
Thank you.
Yes, you in the flower shirt.
Oh, so Neo has some unique hardware. So can you speak to the like system identification and signal field? Any particular measures that you have to use work?
Friction, bandwidth, were big ones. Encoder eccentricity. Those are the top ones I think. You and the glasses? It's a good question. Yeah. Right. I think that to handle very spatial tasks where you need memory, like, oh, where did I put this thing? We definitely need a very different architecture. And we're not sure yet as to whether we want something very end to end, like, just big transformer, or something classical like SLAM, or something in between like VGGT. We're figuring that out. Yep.
Can you rank the census in terms of importance for all these?
On NIA, we need all of them. And I wish we had slightly more. There's very little redundancy on a humanoid, and it's hard to make them redundant. Yep. Not in our current version of our hand. For dexterous manipulation or something, or I mean, you can do a lot with Alohas, and they don't have like dexterity, but they have wrist cameras, right? So I guess it's debatable.
Thank you.
Our next speaker will be remote.
Deepak, can you hear us?
Oh, yes, I can hear you.
Perfect. You can share your screen already.
Okay, just give me 1 second.
All right. Our next speaker is Deepak Thakkar. Deepak is a faculty in CMU and also a co-founder and CEO at Skill. He received his PhD from UC Berkeley, and his research spans computer vision, machine learning, and robotics. He has received of the faculty awards from Google, Samsung, Sony, Good AI, and graduate fellowship awards from Facebook, India, and Snapchat. His research has been featured in popular press outlets, including Humanoids, the Wall Street Journal, Washington Post, Wired, and MIT Technology Review, among others. He has also co-founded Design Map, and later acquired by Facebook's Corporation. And with that, let's welcome Deepak.
Any issues with sharing? You're muted.
What's the problem?
I think he's trying to share.
Yeah.
Oh, we have to stop